Okay, the subject of this Saturday morning science is vortex rings. And these are going to be vortex rings that are made inside of a sphere of water. So first we have to make a sphere of water. And so I'm going through how we make our sphere of water. And here's one method where you gently squeeze water out from a drink bag into a wire loop. And this sphere of water is going to be 50 millimeters in diameter, about 2 inches. And the most amazing thing about when you're making one of these, as soon as you get the sphere so that it fills the diameter cord of that wire hoop, it wants to just hang on to that wire. It likes being there. And you can see it makes a nice lens. Okay, so here's the sphere. You're going to let it settle down a bit so that you don't have a lot of motion in there. So now it's settled down. Here we have some tracer particles in a little liquid drop of water. And watch closely what happens when you put that drop of tracer particles into the sphere. That makes this really cool looking vortex ring. Now, the dynamics of forming these vortex rings doesn't have anything to do with microgravity. However, the environment we have up here allows you to see them a lot better than what you could if you were doing this on Earth. And once the vortex ring moves across the diameter of the sphere, and it settles against the meniscus on the other side, it just sits there. And as you'll see later on in this video, that vortex ring will sit there for well over a half hour during the course of making this video. And of course, if you've made one vortex ring, now what you need to do is make another. So watch what happens here. You can see we're not squirting the liquid into the sphere. When you hold a little drop on that Teflon cannula, the tracer particles, the surface tension forces suck that little drop into the sphere, and that makes an impulse which generates a vortex ring. Now, here's this vortex ring. That's about a half hour later, and notice it's still present there. Now we're shooting in some more vortex rings, and notice they'll move across the diameter of the sphere, and then when they impact the meniscus on the other side, they expand their diameter. And here comes another one. And SOX is the one that's controlling the tracer particles here. So now we're going to try to do 2 in a row. Now this one didn't quite have enough kinetic energy to make it across the water sphere, and notice when it stopped well before the meniscus, and it stayed a rather small diameter, so it didn't have this effect, this blooming effect when you run it to the other side. Now we're going to shoot one going away from the camera, and you can watch the dynamics just from a different angle. Now you can make vortex rings like this if you take an eyedropper and say put some food coloring in it so you have something that's a little different than water, and drop a drop into a glass of water from a height of a couple of inches. The impulse of that drop going through the meniscus of the water will make a vortex ring similar to this, but you'll find that it gets distorted rather quickly. And the dynamics of a drop crashing through the meniscus under the force of gravity is different than the surface tension arguments here. Now watch closely as that little drop, as soon as you touch that little drop on the cannula to the side of the sphere, it just sucks it in. And so it's a different set of forces which are creating this. And now here, Sock's going to resist the temptation of trying to shoot a ring through another ring. So watch what happens. I think that's a pilot thing, trying to fly something through another, under a bridge or whatever. He's going to do it again. Now, here you can see the dynamics going on with a little drop next to the meniscus. Now here, we stick the cannula into the sphere, and we're going to squirt in a little drop of the same tracer particles. And look what happens this way. You can see the dynamics is completely different. It just makes this turbulent stream mixing in with the body of the fluid. Here we're going to do it again. So there's something special that happens when you take a discrete drop of tracer particles and let the surface tension forces suck it in through the side of the sphere. That drop of material keeps its entity and it forms a vortex ring as it moves across the sphere. Now here we've got a cannula hooked to a syringe, and all we're going to do is gently puff on the side of this 50 millimeter diameter sphere of water and get it to rotate. And since we have it filled with all of these old vortex rings, which are now starting to get a little diffuse, you'll be able to watch the pattern of rotation develop inside of this sphere. And I found this interesting. And it's a real small acceleration force that you're putting onto the side of this spherical blob of water using the cannula, and it's just slowly diffusing the momentum into the surface of the sphere, and you can see the viscosity slowly move down towards the center, moving the inner layers of water. We're slowly getting the spin up. And here we have it spun up at a fair clip. And you can see the pattern developed, and this is looking down the axis of rotation, is not that much different than what you've seen in the two-dimensional films we've showed in the past. However, the dynamics is quite different because this is a true three-dimensional flow condition where if you use a thin film of water suspended in this loop and you get the circular motion going, it's restricted to the plane of the film, so you have a two-dimensional problem. And here we have a side view showing that indeed you have three-dimensional fluid dynamics going on in there. So if it's just simple rotation you want to study in a viscous fluid, it might be easier to use a two-dimensional film, and the modeling becomes a lot easier. But if you want to look at a three-dimensional system in spherical geometry, why, gosh, here you have it. And that's it for this last weekend's Saturday Morning Science.